Hello everybody and welcome to the part 3 of the Building Programming Language Infrastructure with LLVM Components. My name is Vassilev and I will guide you through a bunch of tutorials and examples to get you started with that part. Unfortunately, I wasn't able to attend with you and this is a recording. Before we going in more details, I would like to talk about several concepts. So how we can turn, you learned a whole bunch of things about the incremental infrastructure, how we can attach just-in-time compilation to your project. And today I want to spend a little bit more details about Clang and how to use Clang as a library, how to use incremental compilation within Clang, how to build a mock C++ interpreter, and then we want to go a little bit further than that and how to interoperate between C, C++, and Python on demand. So let's get started. First, what is the Clang project? The Clang project is the C, C++ frontend of LLVM. So it's a compiler that supports C, C++, Objective-C, Objective-C++, and other frameworks like OpenMP, OpenCL, RenderScript, CUDA, SQL, and HEP. But what normally people think about Clang is that this is a binary, and that binary would feed it some information and we'll get something out of it. However, Clang is more than that. Clang is more like a platform where we can build tools on top, just like the LLVM. Clang is built of a set of reusable components and can be used as a library as well. So if you look into Clang structure, we'll see a bunch of libraries: analysis, AST, basics, cogent, parse, lex, sema, index, the driver, which makes actually the bunch of libraries into an executable, and then we have like front-end tools and interpreter. So today we're going to use some of these libraries, not all of them because there are too many, but you're welcome to have a look at what they do and how they could be reused in your particular use case. So before we start, now you learned about the Kaleidoscope language and you learned about how to have like a clear separation between a front end, a back end, and an AST and so on. So the canonical pipeline of the way that Clang works is that it takes textual form of C, C++, or other languages that it supports. It goes through two major phases. The first one is the front end, which chunks the bits and pieces into a thing that will be easily analyzable by a machine, and that's commonly known as a front end. And then the code generation part, which produces the LLVM IR, is commonly known as a backend. And those parts are relatively separate from each other. So once the front end is done, it produces an AST, which you probably learned. That's an abstract syntax tree from the previous parts of the tutorials. But now we will have to unlearn it in the context of Clang, because the AST for Clang is neither abstract nor syntax nor a tree. It's a very concrete semantic directly acyclic graph. But for the common terminology, it's called AST, and we're going to use AST here when we mean that. Then this AST is passed to the cogen, which goes over the AST and figures out the kind of LLVM IR needs to be produced. And then on top, this IR then gets optimized and lowered to machine code and so on. So we can use all the great features from LLVM. Now, as a part of exercise 1, I would like to make a baby step here into how we could use Clang as a library. So for that, we will be using two major components of Clang. This is the AST component and the tooling component. So in that exercise, we'll be extracting some documentation from a source file. where, as a rule of thumb, we can use Clang as a library, exactly in the same way as how you would use any other library. So we will have like a bunch of includes. In these cases, we want to extract comments from code. So there is this comment.h. Then we will have some operations on templates for the fun of it. And then we will have some use of the tooling infrastructure. That's why we need to include tooling.h in our program. So this is a very common for every program that we want to embed Clang in. There's a bunch of other things that I'm going to show probably in a bit. And then you can see here, it's a very simple way to instruct Clang through the API. So we have like a bunch of code that we want to pass, and then we have this interface called build AST from code with arguments. So here I'm not passing arguments just for the simplicity sake, but it would take a string, a bunch of arguments around the compiler infrastructure, and give you an object, which is called an AST unit. So it's like a piece of AST. Then we can use this AST unit to get the AST context. This is like a major object in Clang, which deals with allocation, deallocation of AST nodes, and so on. And then we want to get the top of this directed dicyclic graph known as the AST. And this is done by get translation unit decal. Here, in this very particular example here, because it's simple for the slides, I can say tu dump. So most of the objects in Clang, in the same way as LLVM, they have a dump operation, which would print some of the things that's easy for debugging and understanding the data structures themselves. Now, as I've mentioned here, this routine from tooling would run the compiler on given code, and the outcome would be this AST. So the AST in Clang looks like that. You will see here, without even knowing what's the code, you can just take a look. We have like a template specialization decal that's connected with some template parameters. And here the most important part that I guess we care about is the full comment. So there's a bunch of AST for the comments itself. They're Doxygen style of comments. Now, I would propose to, before moving on, just to step out of the presentation and go to the actual examples. So you can see here we have a repository that's set up. Lang and Sunho have probably covered most of this. So the repository is under compiler research, and there's the PLDI tutorials 2023. So it's organized with a GitHub workflow, and we have a bunch of examples here that we're going to run on a machine. So here I have cloned the repository on a Unix machine, and I will be showing most of the examples on a Unix machine. And I'll make sure at the time of the recording, we don't have support for Mac, but I'll make sure that in the little remaining time I have, we will support that as well. So here you can see the directory structure. We have like a build directory. We have configured that with LLVM the way that you have already discussed. And we can just type make and then use some more cores. We'll start building all of the examples because I'm lazy and don't want to do it one by one. There's the linking step, and once we are done with that, we'll see part 3 of the examples. So you can open the first example. So let's go to examples and then P3 example 1, then P3 example 1 CPP. And you'll see the file here. We have some code which can very well come from a C++ file or from any file that Clang can parse. Then we have the codes that we have just shown. And here, if we can go back to the AST, we will see we have like a template, and then there's a record decal, and then the comments is connected to the record decal. So what we do here is we scan through all the decals that are connected to the translation unit. Try to find which is the class template decal. So basically this one. And then we go on and then strip the comment. So we know that this comment is connected to a full comment, and then it's followed by a paragraph comment, and then the textual part comes after. So the Clang has a native support on Doxygen style comments. So this is the Doxygen documentation style, and then you have parameters and then other Doxygen directives. Clang would form the EST, and you will be able to access it. So let's try our first program. So it's always in bin p3 example1, and here we have like a successfully scraped for this particular comment. This is a very rudimentary example, but it's somewhat useful when you want to harvest a bunch of documentation, spell check it, or like change the style and so on. So let's go back to our presentation. I need to fast forward a bit. So we won't have too much time for questions. I will be connected to Zoom towards the end of the session. So if you have questions, please take note of them, and then you can ask them in the end of the presentation. So in exercise 2, I would like to draw your attention to what we can do in terms of more advanced use cases for embedding Clang. And here we have two components, which are the front end of Clang and the interpreter component. So in that exercise, we're going to build a simple C++ REPL in a very similar way to what you have already seen with the Kaleidoscope REPL and the JIT. But before that, I want to talk about a little about incremental compilation in Clang, because this is a relatively new feature. So the canonical use of C++ is to have this embarrassingly parallel compilation, where we have a translation unit that's a CPP file, then that includes a bunch of .h files, and then it forms like a big text blob, which then gets compiled. So what if we can split that translation unit into chunks? So assuming that we have one single translation unit that always grows towards the end of it, would give us an opportunity to continue extending the AST incrementally. So when the user puts some more code, then we can attach it to the existing translation unit in the end, then integrate it, and then recompile it or compile it. And these are called in the terminology of Clang partial translation units, or PTUs. So if you have like a REPL, our execution session starts with input 0, then we compile it, then the user starts typing input 1 and compile it, and then so on and so on. And this is the so-called ever-growing translation unit. Now, processing a translation unit in C++, because of the semantics of the language, can extend an earlier partial translation unit. That happens in template instantiation mostly, or the way that we handle inlines, or the way that we deal with the argument-dependent lookup. But I'm not going to dive into details here about that. Another thing that I'm not going to talk about, but it's very interesting, is the way that because it's a REPL and users can mistype something, we should be able to somehow recover from these errors. And this is a very interesting topic here that I'm not going to cover in this particular session, about error recovery or undoing code or undoing executions. Here the partial translation unit logic helps a lot, because it helps us to clean up the compiler infrastructure without killing the session. Anyway, so going a little bit further in that, the way that we would build it, it's very similar if you look at it to the way that we saw in the kaleidoscope, with a few notable exceptions. For example, we have a incremental compiler builder. So here we ask for Clang, we ask Clang to create a builder class and then set a bunch of compiler arguments. Here we pass -acd C++20, which means I want the C++20 standard mode. Another very interesting thing is the -f plugin option to Clang. So here the -f plugin and the Clang plugins are facilities that could be loaded dynamically by Clang. And here in principle what we could do is you could build your own extension that's very tailored to your particular use case or code base and attach it to your incremental compiler. So every time that the incremental compiler sees the partial translation unit, it will give control to your plugin infrastructure. And this is very useful for developing domain-specific plugins. We're not going to have time to look into that, but it's a very interesting and well-documented feature in Clang. It's tricky to write these plugins, but they're very useful for different purposes. Of course, here, if you want to build a C REPL, not a C++ REPL, we just need to pass -xc, and then that would enable C instead of C++. Then what we need to do next is, once we have our builder class, the next thing is to call the create CPP routine, which creates a compiler instance that's ready for incremental input. Like it makes a bunch of changes to the default compiler instance so that it can consume input incrementally. And the last step is to create a interpreter object. So inside Clang, we have also an interpreter infrastructure, which essentially turns Clang into a interpreter. And here interpreter is a little bit broad term. It's not an interpreter per se, because we're not going to interpret line by line or like instruction by instruction, but actually we're going to have more towards more like an incremental compiler, where it's able to consume chunks of code, JIT them, executes them, and then consume the next chunk. And here I think it's important to say that some people think canonically that C++ is compiled language or Python is an interpreted language, but whether a language is compiled or interpreted, it's a matter of implementation choice. So Python can be compiled, C++ can be interpreted as well. Now, from the language design perspective, given the fact that you have only compiler for the language or only interpreter, then you make different design choices, which would make the other approach easier or more difficult. So, for example, if we know that we compile things statically, always ahead of time, we don't bother too much about, for example, translation performance, how fast our parser is, and vice versa. So sometimes when we optimize our language for REPL use, we focus on how to save typing of people rather than performance, for example, because we have this REPL while people are typing, then there is a lot of latency that can be hidden behind that. So the next step, once we have the interpreter created here, we create the line editor. Here I put like PLDI CPP REPL, and we can read line by line the input, and then call the interface parse and execute, passing the input. Now this is a very basic example, but you can see here that we can have the so-called meta commands like quit and so on, which connect to other Clang components. So for example, we want to be able to load a library. So we want to say, okay, we want to load this dynamic library so that we can resolve symbols from it. Then we can add a new meta symbol here and call DL open with that library. Or we can implement it as a pragma handler. For example, we can say pragma PLDI CPP REPL load and then the library name. Then we can react to this. We can easily develop this pragma handler, attach it to Clang as well, and make this programmatically trigger. Let's take a look at our actual code. If we go here, go back again to examples, P3 example 2, we'll see it's very easy again in terms of like code written. You have noticed that we have this LLVM shutdown object, which makes sure that it shuts down properly LLVM towards the end of it. So this is this RAII object, which you can see in the many places in LLVM and Clang, which uses this idiom where once the variable goes out of the scope, then the destructor gets called, and then we can perform some actions on top. So here in that case, when the constructor is called at the point at that point here, we'll do some initialization part of LLVM, and when it goes out of scope, we will do some deinitialization part. Anyway, here I think the important part is we need to initialize a bunch of native targets. So the way that LLVM would translate our code to machine code. So here you will see the compiler instance being created and the example. So here we want to detect if there are some errors, and if there are errors, we want to log them and report that we had error and then exit with one. So if we see how that's going to behave, then P3x2, and we have a C++ level. So we can do like extern C int printf. We can basically forward declare printf and then say auto r equals printf hello world. Hope I didn't misspell that. You can execute it. That goes to the JIT executes the static initialization, and so on. Now, without going into too much details, Clang has a special extension when it's in such mode, so that we don't need to write declarations all the time so that we can get something out of something executed. So we make an extension to C++ to support statements on the global scope, and this is called the top level statement decal, which essentially allows us to execute non-standard C++ code. For example, printf top level like this. Now another interesting thing here in the REPL is that, of course, we can do errors. Let's cause an error here. See reports, it still goes on and so on. So this is the very basic REPL that we could bootstrap literally with less than 100 lines of code. Let's go back to our slides again. Yes, what here we do with the REPL is we tell the interpreter to add a new partial translation unit. So we say, hey, interpreter, we got a new input. Just incorporate it in what you already have in your session. And this is the interface. Now, we saw that the canonical pipeline that goes through the backend and the front end, and then to the front end and the backend and the LLVM IR. Here, the classical REPL changes that a little bit. For example, in the what we saw in the demo that I showed is that we got text. We went to Clang REPL or our PLDI REPL. Then we used Clang as a library or Clang as a service to process that text, and we got an AST back. Then we didn't show that in the example, but in some cases we need some transformations on this AST. One very notable example is when we want to print results or when we want to deal with CUDA code. Then we get the transformed AST back, and we send it again to Clang, to libclang. Then we get, because it piped it through CodeGen, we get an LLVM IR. And this LLVM IR then gets down to the JIT. And the JIT takes care of lowering to the specific target, here x86 or NVPTX. And then that gets executed on a CPU or on a GPU. So you can see here we changed a little bit the canonical compilation pipeline. So here you can also see a line that I'm not going to talk about too much, but this line here that connects machine code from the interpreter. So this line essentially allows us to embed the interpreter pointer inside its runtime, and that would allow us to implement facilities like eval. So inside some of the interpretative languages, you have this eval operation, which is like a function code that takes more input. So this thing here is allowing us to do something like that with C or C++ REPL. Getting a little bit further in terms of complexity, what we can do here with Clang is exercise 3. Now that we have things that are compiled and things that are interpreted in C++, how do we make them talk with each other? We're going to use the same libraries here, but I would like to introduce a special object that takes care of this. So before going and showing you some examples, I would like to talk a little bit about what we saw here. So we started incorporating components of Clang inside our programs. So we can have like a C++ program that does something specific, and then attach an incremental compilation part of it because we want to specialize certain parts, or like we have like a library that we want to extend a little bit, or we want to use optimizations that are available in the JIT that take into account the specific parts of the runtime behavior of the program. But in essence, we use the compiler as a service. So we don't use it as a binary anymore, but we use it as a service, something that we could query when we needed to and then get some results back. And here in that example, we will demonstrate how we could transport results from compiled to interpreted code and vice versa. So in order to do that, this means that we need to have like a wrapper that wraps some memory around and possibly takes the object lifetime from the C++ runtime. So the C++ semantics sometimes assume that some expression needs to be destructed in the end of, basically when seeing a semicolon. But now that we want to transport that and it came from the interpreter, we might want to extend its lifetime. I'm not going to get you through the nitty-gritty details on this, but if you are interested in that, you could follow the pointers in this slide, and you'll see it. So sometimes, depending, because the C++ language semantics includes non-assignable types or const types and so on, we also want to have some front-end support to take the execution result of objects that include non-assignable operations, non-assignable semantics. And this object is the so-called clang value. So the clang value has a property of holding in an efficient way some memory that's ref counted and has small buffer optimization to be able to transport the results. So that means that we have a very small object, because it's going to be used in hotspot, which counts the uses and only destroys the memory when there is nobody using it, and it's very optimized towards like built-ins and small items that we normally exchange. And we also wanted to support pretty printing, because you can say in the repo environment we want to be able to map the high-level AST type to the actual memory. And this can be done in that way because we hold these two elements in the clang value. And of course, since it's hidden behind an indirection, we need to be able to perform conversion operations. Because, for example, if the interpreted code got us an int and we want to use it as an unsigned, the compiler has no way how it can generate the relevant instructions. So we need to be able to, the clang value needs to support converting the low-level bit representations. And here you can see more in Jun Zhang's presentation and the related RFC that was sent to the LLVM developers list. You can click, these links are clickable, so you can just follow them on the bottom right on the slide. So how do we bridge the compiled and interpreted code with the compiler as a service? So as you saw, we allocate a clang value, which then we pass to our parse and execute interface. So you can see here we define a function that's called an extern C function that's called square, which obviously there's a square of the input. And here the second statement is a top-level statement declaration, which here doesn't have a semicolon, which hints us that we need to get this result out in the value. And then we pass the value itself to the interface. And that's pretty much what we need to do. Now, in our compiled program, we can call printf and say, I know that what's in here is an int. Give it to me as an int and then print it as an int. Assuming that we wanted to get it as a float, we need to say convert to a float, because then this would trigger the right semantics. Or the other way around, we could just query the JIT the way that we did it in the Kaleidoscope tutorials and say, hey, give me the symbol address for the thing that you compiled with the name SQ. It's a little bit more tricky when we don't have extern C, because if we didn't have extern C, we needed to, so C++ has this mangling scheme that would put extra semantic information for the linker to figure out what's what. And this name would be very difficult to find out. So for C++ here, it doesn't fit on this slide with like 2 lines. Instead of passing the SQ as a text, we would have to find the declaration of SQ, meaning that we need to say interpreter or clang, make a lookup SQ, give us a declaration, and then pass the declaration pointer, and then internally the interpreter would mangle the name and give us the symbol address. And here, again, we have the simple address, we know its signature, and we are going to define a pointer to this function that was just compiled within our code. And then call that with our compiled code. So all of this here that you see is compiled. And our compilation pipeline, our compiled code is able to go into the JIT. But let's see how this works in practice. First, let's take a look at the tutorial. P3 example 3. P3 example 3. The same, now probably boring stuff, initialization of LLVM, setting some compiler flags, creating an incremental instance, and we say parse and execute here. Just for the demo. And here we can pass the value as part of this parse and execute, so that it captured the square interface. And that's pretty much the same as what we went through. And here, before diving into the example, we have like a very interesting point, because one of the most challenging points when it comes to connecting other languages to C++ is the fact that it's horribly complicated language, and it has like several languages inside it. One of it is the Turing complete template language, and most of the interoperability problems have been coming from the fact that we can't really understand templates. So because the templates are such a beast that they can work with user types, but the library authors would not be able to provide the specialization or instantiations for the user types, and they need to like enumerate all possible things that the users might need and so on. So here with that infrastructure, the way that we're doing this here, the obvious question becomes, can we actually instantiate templates on demand? But let's not get ahead of ourselves. I want to show you first this example, how it works before moving on. V3. So we see here that gets executed. So we got the printout, we got the result from value, square of 12 is 144, and we were able to call the same function from compiled code. Pretty nice. Let's go back to where we are. So speaking of getting more and more out of this system, one obvious of the steps become what we can do with the compiler as a service beyond the C++ language. And in the exercise 4, we are going to do two things. We're going to try to use the compiler as a service within C first, and then within Python. So let's get started. We talked about programmatically instantiating C++ templates, and this is a big deal because sometimes you can have like a library and then you define outside of the user type a user type, and there's no way how the library would know which are your user types, and it's very hard to do it without having an infrastructure that allows you to instantiate a template on demand. And there has been proposals to the C++ language for an extension of that size that the C++ committee is looking into whether or not to support some part of JIT compilation to solve that particular problem. So for the example 4, we want to create a library this time with compiler as a service blocks that create some interface of that library so that we can use it. Then we want to build a C binary that can programmatically instantiate and call a C++ template function. And then we want to wire that infrastructure to Python via Python standard facilities. So let's get started. So we'll see that in P3 example 4-lib, we have a library that's capable of instantiating a template. I'm not going to go through the particular implementation details, but let's have a very basic API here. We have Clang parse, which gets some code and parses it. We have Clang lookup name, which takes a name, takes a string, and then gives us back a decal or an AST pointer, a pointer to an AST node. We have a get function address, which takes a string or a decal and gives us a location where we can call this function. We have a create object, which is a little bit difficult to explain, but here the point is that this takes a decal, like a declaration, and programmatically allocates storage for it. This is the equivalent of calling new and then some name. And of course, we have a Clang instantiate template, which takes a bunch of arguments and a decal. So how do we incorporate that library? Let's first take a look at the library. It's nothing glorious here. It's examples p3x4 lib.h. Here I've made it work with C and C++, so if it's C++, we basically enable this, and then for C mode, it's just what we show on the slides. I'm going to go through the implementation of the library, but just to show you that it's not like a humongous thing. It's 140 lines of course, non-trivial code, but yeah, it's manageable. It's within reach in terms of understanding if you're a beginner even. Let's get back to the slides. So then we can have like a binary, which is written in C and take some code. That code, for simplicity, I have hard-coded it as a variable, but it can come from a file, a bunch of files, like you name it. Here, the important part is that we have a class A and a class B, and inside that class B, here, we have a templated function, which is called callMe, and it takes a template argument. And what its body does is I was instantiated. It tells us, it outputs, I was instantiated with the type ID of T. So the type ID of T is like the compiler internal representation of how the type is named. So we will see a weird name in the end. Now, the next thing is how we build the binary. We use our library, we include the header file, then we say parse this code that we have just shown, find the template class, you see here, B, will get a pointer to an AST node. Then we'll get another lookup for T, which is the A. So we're going to instantiate the template with a class A. And then say instantiate template of that template class that we just found. The function is called callMe with a type of, here I probably misspelled it, it must be A here. And then the usual thing, if we want to run it, then we make a function pointer and then say ask the JIT about the function address of the instantiated and compiled function. And then have this callMe fnptr, which in that case we create a new object of type T. So this is the equivalent of calling new of A. And then we just call it with that parameter. And that's it. You can take a look how it works. We are a little bit ahead of, we're a little bit late, I think. So going back to the example, can show x4.c. Note this is a C thing. It's compiled to the C compiler. So see here in the code, we have what we showed in the slides. Here I try to simplify that. The instantiated arguments, it's an A here. See, my slide is just broken, not my code. Here I have extended it a little bit to demonstrate, and I'll demonstrate it. I'll demonstrate the power of this to you. So here we can add a few arguments to the binary, and then it will be able to instantiate with our custom logic. So if you go here, binary p3 x4, we run it, we will see that here it called the function instantiated with A. But here the first argument, I can add another argument, which is class my class, like this. Say my class, say class pointer. That tells us that parse this code, this extra code, the type, find the type my class, and then make the instantiation with a my class pointer. If I run it, it says it's instantiated with pointer of my class. I can do a reference and see it's gonna change. I can do what? Pointer. See pp here. So it took my custom input in C and instantiated the template that came from C++ within C with my custom types. It's pretty nice. Now, what we can do further is, since that works in C, it can work with probably other languages. And here we want to make a demonstration about, of, with a language such as Python, which is dynamic. So it's not like a language which follows pretty much the same semantics or the same rules and so on. So we're gonna see this instantiate CPP template PY, which instantiates C++ templates on demand with Python. Here the important part is that when we query information from the Python interpreter, when we used to do Python bindings, we would again enumerate in the same way all possible types, all possible values, and then hope for the best. Here, when we have this reactive infrastructure, which allows us to have an interpreter-like object that would give us C++ information, we could do that on demand. So basically, whenever Python wants something, it could just go to the C++ interpreter and say, oh, I need this thing, and you go instantiate it and give it back to me, the information, including documentation, for example. If you want to interoperate with C++ from within Python, the first thing that you probably want to do is to port the documentation, the C++ documentation, to the Python style documentation for your users to be able to see what things are doing there, things are done to this docstring or whatever it's called in Python. So here in this example, we're going to show how we can utilize this library via the C types. This is the facility in Python, which is a very rudimentary to be able to call like things into C libraries. We're going to build a Python wrapper API for the functions in P3 in the library. That's for making it easier to use from the Python side. It's not like it's a necessary step, but it makes the code nicer and more Pythonic. If these are basically several items. The first one is this interop layer wrapper. This is responsible for instantiating the C++ templates. Now we're going to see how. Then there's a template wrapper, which takes care of finding and matching the C++ template arguments. and the co-CPP func facility, which is a small class which wraps the low-level JIT function pointer calls. So let's get started. So here we have the C types information that we generally offer. What we are going to do, this code snippet here would load this shared library as this lib interrupt. And then the C types would allow us to describe what the function's signatures are. So for example, you see here that we have this clang parse. And we tell Python that this gets mapped to underscore CPP compile. And the argument type of the CPP compile is a const char pointer. And it has no return type. It's a void return type. And the same way we enumerate the rest of the functions that we want to use from that library. Now the second step is, you probably saw already, it's the same thing. This time B derives from A, and we have the same template that takes two arguments, T and U, and then it does a printf, right? So this is the part which we can spend a little bit more time in explaining, because it's an essential part. This is our interoperability layer. For the purpose of that presentation, we're going to consider it as a black box. Here, Python allows us to provide types which have their own way of construction. This means that here I'm saying the CPP-A class is of type A, and whenever somebody wants to use it, then we say get scope of A, which means make a lookup, connect it to the AST chunk, to the AST pointer of the C++ runtime. And similarly, when somebody creates an object of that type, we say allocate. This is the same thing, the same function that calls clang allocate, where we would allocate storage and we would create the object of type A. The same thing calls for B. Here for B, it's a little bit more complicated, because we say, okay, this is a new type for B. It inherits from A. We already have a handle to. We already know what A is. Here it's CPP-A, I'm sorry. And the handle is this one, which makes a lookup to B. So we make the connection. Pretty similar to what A does on the new part. And here the important part is when we say call me. So if cpp-b.callme gets called, we handle the control to this template wrapper and say instantiate the template given the arguments of call me and of that handle. So this gives you a way how you can model the C runtime in a very Pythonic way. So here in that line we create A of type CPP-A and B of type CPP-B. And when we want to call the C++ function, we just say b.callme, and then we have two ways to call it. One is explicit template arguments. So basically here the facility, the template wrapper facility would go and split these template arguments and instantiate with these concrete items, and then pass these two parameters to be able to call it. Or we can rely on the implicit template instantiation logic by just not specifying anything, and then the deduction process would tell us the underlying types of these two things. Okay, so let's move on to our next few slides. So we saw the interaction of C++, and I wanted to maybe talk a little bit about the opportunities that this opens. So for example, normally when we talk about an application, we have a bunch of phases: development, deployment, start phase, and execution phase. Normally when we develop code as users, we develop with abstract machine and abstract user base in mind. So, but generally what we want is we want a very concrete user and a very concrete machine. So generally the static compilers are targeted to assume some abstract machine, to make some optimizations based on that assumption, but that doesn't that's not probably enough in terms of what we could employ in optimizations, or what we could enable as if we had a compiler as a service. And here I wanted to enumerate several points where we could apply continuous optimization and better integration between the static compiler and its actual runtime. So the first one is when we produce the binary. At the point where we produce the binary, we could make certain assumptions about that binary. Then when the binary started, this is the phase where before the binary started and after the binary is produced, this is the ahead of time compilation that we could make some assumptions at least on the machine that we're deploying. So the machine that we get our binary deployed is the one that is to run the binary, so we can assume certain things there. The same when the binary has started and before it's executed is the just-in-time part where we could optimize things and use the JIT to speed things up. And then once the binary is executed, we have this continuum that we could use to collect the behavior of how we use the binary, and then incorporate it and help the optimization of that binary with the JIT. So you saw how we could re-optimize binaries and so on, but we need to be able to collect some data. And here, when you see it, you can see it in two ways: as an optimization opportunity, but it's also a defer opportunity. So for example, the static compiler, when it doesn't know information about where it's going to run, what are going to be the types that we use and so on, it could decide to defer that information to the compiler as a service, because it's going to have that necessary information at the time it starts. And vice versa, we could use that information that came from execution profiles and so on to optimize it, but optimize it smartly. And the profile guided optimization goes a little bit in that direction, but it's not well connected with the JIT just yet. Yeah, and that being said, I have 1 minute for you that I would like to, maybe for the curious ones, to show, to go through quickly a bonus exercise, and it's pretty much how we could build a simple CUDA REPL with the same infrastructure. I'm not going to show you how. The code is inside the repository. The ones that have CUDA devices and are interested can download it and test it out. So it's very, very similar to the way that we set up our interpreter. So we again use the compiler builder. We again use the a way of creating the incremental compiler, but here we want to say what is the offload architecture, in that case SM and the 35. And this time, instead of creating a single compiler instance, we need to create two compiler instances. One is for the device and one is for the host. And then we want to pass it to the we want to pass it to the interpreter pointer construction here. I clicked one too many times. And we're off to the races. We could execute CUDA and C++ code. So we could see real quick. P3 X bonus. Can run it, and it takes a long time because I have a CUDA device that's connected to my USB, I think, and the transfer of data is rather slow, so it takes a bunch of time to execute the device code, but yes, we can see it here. Then we can probably real quick take a look at the examples P3x bonus, then P3x bonus. You see it's pretty much the same thing. Here we have a bunch of jumping around to find the CUDA header files, but we have this host code, which is very basic, and we have this device code, which gives us an opportunity to be able to kind of on demand run CUDA code and schedule that. Yes, so that being said, I think I am at the hour now, and I would like to thank again for the opportunity to give these presentations, and I hope you liked it.